Okay, the last thing I want to mention here is the concept of friction. In particular, we're looking at a certain type of friction that is either referred to as column friction or dry friction. It is different from viscous friction, that is more a fluid related effect. Whenever two surfaces rub against each other, there is this column or dry friction that kind of have resistive effects. It is actually one of the most difficult forces to properly characterize, but we can do rough approximations, and you encounter this in many of the problems in this class. So it's a good idea to carefully think and develop these descriptions. Consider an object sitting on another surface, and you're pushing on this object with some force F. You can also go ahead and try to experiment. You have seen it. As you apply very little amount of force, you will notice that your object, for instance, your phone and sitting on the surface of a table, does not move. If the force is very little, you're applying forces, so force is non-zero, but you end up with zero acceleration. What is resisting that motion is dry friction. And as you start to increase the force, at some point, the object starts to move, and again, you feel this resistance of friction. In fact, there are two modes or regimes in column friction. One is a static friction. That is what happens when there is no motion between the two. So no sliding between the two surfaces. So in this case, because object doesn't move, acceleration is zero, it means force of friction, force of static friction, the magnitude of it actually, the magnitude of that force equals to the size of the external force you are pushing it. To see that why it is the case, consider the box. I want to study the forces. This is the external force F you're applying. I want to draw the free body diagram of this box. So I feel this resistive force, let's call it Fs, F of a static friction, acting at the boundary of the box, the object, with the other surface, like the table. And note that there's also possibly gravity acting on it if it's a horizontal table. And because the box is pushing on the table is pushing it back, N. And just looking at the horizontal direction, you can write equations of motion F minus Fs, because they're in the opposite direction, equals mass times acceleration. You always calculate static friction equals the size of a static friction equals the external force pushing on the body. So that is the magnitude of friction force. The direction of static friction is always in a way that it opposes sliding. So to find that, you have to figure out all the net force of all these external forces, what direction those net forces are acting. The static friction is opposite of that. So what happens, we saw in our experiment with the phone, that as you increase the force, external force, as you increase this, maybe let's write it, do it here. As you increase this one, you feel more resistance. The force of static friction increases until a breaking point. And that breaking point is where the static friction can no longer maintain a stationary position. So there is some maximum value it can sustain. And that value is dependent on the two surfaces. Some surfaces are more rough, they have more friction, if you will. Some are smoother. This coefficient is depends on what surfaces the sliding is happening, and also that depends on the compressing forces that is compressing the two bodies together. So whenever there is this compression force between two surfaces, you have the chance of creating static friction, and the maximum value of that can be calculated using this equation. As soon as the external forces increase this amount, the static friction essentially breaks, that the object starts to move. One thing I want to be very explicit and careful here is that magnitude of static friction is never this amount. In fact, the magnitude is always equal to the magnitude of the external force pushing on the system. What you calculate using this equation is the maximum value, and as soon as the friction force reaches that maximum value, it actually breaks. The object starts to move, and then you enter a different regime of friction called kinetic friction. So when static friction breaks, now you start to move with some velocity, possibly accelerating too. Now in this case, so here v was 0. In this case, if you draw the free body diagram again, you have the external force. What color did I use? Red. You still have some friction. You still feel the friction of the table on your phone. Let's call it Fk to make it different. Still, possibly you have gravity and normal forces. Let's call it mg to be better. All right. So when there is motion, if there is sliding, in this case, you can go ahead and calculate the size, the magnitude of this kinetic friction as, again, some coefficient of kinetic friction multiplied by the compressing force between the two surfaces. So this is the magnitude of the force, magnitude of kinetic friction. And where is the n? Kinetic friction force, the direction is in a way that it opposes direction of sliding. So if a surface is sliding to the left relative to another one, the force is, I forgot. If the sliding is to the left, force is to the right, and vice versa. So it's always opposing to the direction of sliding. To see that, actually, let's make the diagram a little different. So this is, for instance, our table. This is the phone. You're pushing on it. Because this sliding is in that direction, on the box, the force is the opposite of that sliding direction. You can also look at the table. This is the table. There could be some forces from the ground. I'm not going to draw that. But the object that was here is sliding in that direction. Or from the perspective of this box, oh no, that's not the right color. This sliding happens, the table is sliding beneath the box. Yeah, that was good color. In that direction. So the force of friction on the table is in the opposite direction. It makes sense because, first of all, it is a action and reaction. Force of the table on the box is to the left. Force of the box on the table is to the right. Same magnitude, opposite direction. Also, intuitively, if you have a lot of friction and you start pushing, you may end up pushing the table to using that friction force. So the force of friction is in the direction of your pushing on the table. So, all right, that is all the forces, at least the common forces we encounter in mechanics. There are so many other forces that we don't try to solve solve systems that have those forces, like the aerodynamic drag and viscous forces and electromagnetic forces. And yeah, there are all other kinds of forces. But in mechanical system, friction, spring, gravity are the common ones that we deal with. So we'll see a lot of examples involving all of these. And I have a tiny bit left, I think. And that should be enough for this chapter. So I'll do that now, later, I don't know. I'll record it. Let's see when I post it. All right, see you then.